Aloha, biostatisticians. Let's go through the Lab 11 on logistic regression for our class survival. I'm going to assume you've already downloaded and saved the notebook file that I emailed you, and you've put it into a folder along with the updated class data that you've also saved in the same folder. It should look something like this. I put it on my desktop and I call the folder Lab 11 Logistic Regression Class Survival, but you can call it what you want. Inside that folder, you're going to have class data as an Excel spreadsheet or a CSV and the RMD file. That's the R notebook. If you open up this R notebook, you can see I've already got R open, so it opens up really quickly. Got it? All right, good. We'll go straight into it. We'll get through this, all right? The introduction. Remember from the last class that logistic regression is a simple way to do linear regression on a binary response variable. In this lab, we'll analyze our own survival data in the same way it was done for the Titanic data. We'll play a game called Bears, Cowgirls, and Ninjas to determine who survives and see if there is a relationship between our survival and our sex and age data. Be sure to type the response to prompts where you see the symbol. First thing, question. What is the question? How would we phrase the question that we're asking here? Well, we're going to be using survival as the response variable and sex and age as the two explanatory variables. So how would we phrase this question? What are we trying to figure out? How is survival affected by sex and age, right? Now, if you go back to our two-way ANOVA penguins lab, the questions here are phrased really well. You can just look at how that's done and just put in new variables. If I scroll down here to questions for two-way ANOVA in the penguins lab, here's a nice way of putting it. Controlling for the species, is body mass significantly different between the two sexes? So if we just change the variables around, we could say controlling for the age, is survival significantly different between the two sexes, right? And then for the second question, controlling for the sex is now not body mass, we have a different Y variable, is survival significantly related to, right? Because it's another numeric variable. So is it significantly related to age? And then 3 is the relationship between, in this case, not species, it would be age and survival different for male and female students instead of penguins. So change that around to make sense. Here's how we can do it. Let's just do that. Let's just take this and we'll put it here and we'll just change it around. Okay. Controlling for the, not species in this case, controlling for age, is, now we don't have body mass, we're talking about survival, is survival significantly different between the two sexes? Boom, got it. Controlling for the sex, is survival significantly related to age, right? And third, this is the interaction, is the relationship between age and survival different between male and female? We're not penguins, we're pretty cute, but students, we're students. So we change that around like that. Got it. Good. Let me make this a little bit bigger for you. Let me see if I can make this display a little bigger for you. I'll make my display bigger so you can see me better. And I'll make this display bigger. View. Zoom in. Oh, weird. My functions are not working on this. Huh, interesting. Okay, and I can't edit this video because I don't have that software with me. It's interesting. Yeah, I can't do that. All right, well, that's what we got. So zoom in, pause it, zoom, take a screenshot, zoom. Okay, hypotheses. Here you need to write the 3 hypotheses for a regression with 2 variables and an interaction term. And we did that with the logistic regression for the Titanic lab, and we also did it with the two-way ANOVA. We also used interaction. Let's look back at our logistic regression for the Titanic lab, because that's a pretty simple example. Scroll down here. How did we write the hypotheses? Did we write hypotheses? We did write hypotheses, didn't we? Here we did. Forgot to write. Let's go back to two-way ANOVA. Better. Two-way ANOVA explains it better. Okay, here's the hypotheses written out for the two-way ANOVA. Let's just copy and paste this over to our logistic regression class survival lab, and we will just change the variable names. So the effect of sex on not body mass, it's on survival, right? Mean, everywhere it says body mass, change that to survival. Mean body mass, mean survival is equal between females and males. That's our main effect for sex on survival. That's the null hypothesis. The alternative hypothesis, mean survival is different between males and females. Boom. Second, the main effect of species, not species, age on survival, right? So the mean effect, the null hypothesis, is that the mean survival has no relationship with age, is not related to age, right? And the alternative hypothesis is that mean survival is related to age. Boom, got it. Okay, and then the interaction between sex and age, that interaction term, the hypothesis there is that there is no interaction between sex and age, meaning that the relationship between age and survival, is the same for females and males. Or you could say that the relationship between sex and survival is the same for all ages, right? Alternatively, you would say there is an interaction between sex and age. Wait, okay. There is an interaction between sex and age, meaning that the relationship between age, survival has an R in it, and not body mass, but survival, is different for females than for males, okay? So that if there is an interaction, it means that the relationship between age and survival is different for females than for males. That's what we saw in the Titanic lab, right? Similarly, the relationship between sex and survival depends on the age, right? That's how we write out the hypotheses, three hypotheses and alternative hypotheses. You can even just put the nulls in here, and that's fine. Okay, collect data. We did that. That was fun. We jumped up and down. I was a cowgirl, and then I was a ninja. It was awesome. I won. I survived. Okay, so then we open the class data Google Sheet. Enter 1 in your row if you survived. Enter 0 if you did not survive. We all did this. If you weren't there, Hey, if you're watching this now and you weren't here, you died. You did not survive. Okay, so download the data into a file called class underscore data.xlsx. If you can't use Excel, do save it as a CSV. I think you already know this workaround. Okay, import the data using the import dataset tool in the environment window. I'll show you how to do that. I think you already know, but I'll show you again real quick. You just go up to the upper right-hand window here and you click import data. And if you're doing it from Excel, you choose Excel. If you're doing it from CSV, I recommend using from text read R option, that second option, read R. It's a little simpler, both ways work. I think it's easier this one. If you're going from Excel, which I am, I choose Excel. It opens up a dialog box. You browse over to the data, and it should be in the place where you have your file saved, which in this case it didn't. And it will automatically show you a preview of your data. And then you go over here to where it says code preview. Copy this data or this code, copy this code, right? And then you can either import it or cancel it. Either way, I'm just going to cancel it because I'm going to actually take that code, put it into this chunk here. It's going to load the library, read XL, and then it's going to load my class data into something called class data, read XL. And I'm actually going to just go ahead and run this code. And I want to make sure it works because when I want to knit it later on, if I don't have this code in there working, it won't knit properly, right? You need this chunk to work for you so that you can knit. And I'm also going to delete view class data because that just opens it up into that other tab as a spreadsheet so you can see it, which is nice, but not necessary, and kind of makes the knitting take a little longer. It kind of looks weird. Fine, either way. Okay, it runs. Good. Right now we have something called class data. You can see we have this thing called class data up here in our data. Now to clean the data, clean the data. I think I'm going to pause the recording real quick. Sorry. No, I'll just do this. We'll do it like this. So to clean the data, we're going to subset the data. The first step is to subset the data. We're going to select just the variables we want to analyze, which is survived. Actually, it's not survived. It's survival. Sex and age. Notice that survival is not capitalized. Sex and age are capitalized, and we'll store them in a new data frame. So if this is the code syntax, this is the general way the code is written. So we're going to copy and paste this template, essentially this syntax, into this chunk, put it in the chunk, and then we're going to say, oh, we know we're going to subset. What are we going to subset? We're not going to subset from df1 because df1 doesn't exist. What exists? Class underscore data, right? And we're going to select, not variable one, what are we going to select? We're going to select survival. We're going to select sex, and we're going to select age. Again, remember to capitalize what needs to be capitalized and don't capitalize what doesn't need to be capitalized. You can keep calling it df2 if you want, or I'm just going to call it class survival, right? Class survival, that's our survival data. Save that in there. Boom. Okay. So let's check the data structure. What are the data types for survived, age, and sex? The syntax for the code is right here. So if we take this code, really simple, just str, and instead of on df2, we're going to substitute the name of the data frame we're using it, class survival. It runs, and we can see we have just these three variables. Survival is a number 0 and 1. Sex is a character, which is a factor. It's categorical. That's what we want, M and F. And age is a number. Perfect. That's what we need. And so we don't have to change the data types. If we did, we could use this code here, but we don't need to. So just leave it there. you can either leave this code, this chunk, you can leave it blank, or you can delete it. You can keep it there for if you want to use this as a template to do analysis on something else later. Okay, remove NAs. Those pesky NAs, the missing values, they got to go. Do we have any NAs to omit? Actually, I don't know. So I'm going to skip that step and go down to this next step. Summarize the data, summarize the data frame. I'm going to copy and paste summary DF2. I know I'm going fast, but you can just pause me, right? And then if you don't need to pause me, I'm not going to slow you down too much. We're going to do summary, class, survival, right? Class survival, run that, and we get our summary statistics. If there were any missing values, we would see NA in this summary stats, and we don't see any. We can also go over to our data here. We can see class survival, and we can scroll down and look and verify, yeah, there's no missing values, right? Because everyone who was missing, we entered a value for them. We got everybody in there. Great. And we can also see that survival is a number, sex is a character, and age is a number. We could also code survival as a character, and it would pretty much work, but this works too. Okay. So what is the mean age of the class? What is the mean age? Well, you can see right here, the mean age of the class is 23.43, right? There it is. There's your mean. I just want to make sure you ran the step, looked at it, answer the question. All right. Count how many students survive. So how do you do that? How do you count how many students survive? Well, you can make a little table, and the code syntax is right here. Copy and paste this code, table, data frame, variable. Obviously, again, it's not DF2, it's class survival. And the name of our variable here is survival, right? Run that code, and we can see that 13 students survived and 10 didn't. It's not quite 50-50 because there were some missing people. Otherwise, it probably would have been 50-50 because, or pretty close to 50-50, since it was like half the class survived and half didn't, but roughly like that, right? How many students survived and how many did not survive? So you can answer that. 13 students did not survive and 13 students did survive, or right? Okay. Oh, 10 students survived. 13 students did not survive and 10 students did survive. 0 didn't survive and 1 is a did. Okay. Continue on. Good. Now check our assumptions. Refer to the class lecture on logistic regression and refer to the Titanic lab here on regression. This goes through how to so we don't really check the assumptions in this one either. I left out doing these assumptions for the logistic regression because it takes so much time to go through that. But we did talk about what the assumptions were, and we've gone over how to check the assumptions for other linear analyses. So just look back on those. We want to make sure there's no multi-collinearity, etc. But we're just going to go through with this so you'll have time to write all the code before the end of class. We're just going to go and assume that the assumptions are correct and or met and analyze the data. So the first thing we have to do is to code and run the GLM model. Remember, GLM is generalized linear model. The code syntax right here, you're going to store your results in the something called results that is that comes from running a general linear model function on your y variable tilde x1 times x2 family equals binomial my data, right? And then looking at the summary of results. All right, let me slow down a little bit and we'll get through this. So copy and paste the code to run the logistic regression model. What are we going to do here? How are we going to make this work? This doesn't work like this, right? If you try to run it just like this, you get an error. My data not found, right? Nothing here is going to be found. You have to change the Y here for our Y. What's our Y? What do we want to predict? Survival, right? We want to predict survival. So we type in survival. What's our X1? Our X1 is sex. And our X2 is age. You could switch it around and make it the other way. But we have it like this in the data. That works. Sex and age. And we're using the asterisks here to indicate that we're crossing these variables. So when we run this analysis, we're actually testing three different hypotheses. We're testing the main effect of sex, the main effect of age, and the interaction between sex and age, right? And this is one of the cool things about GLM is that we can specify the family. Up until now, we've always assumed we had a Gaussian or normal distribution. Not anymore. We can say, no, we have a binomial distribution. That's what we've got. And our data is not called my data. Our data is called class survival rate. Now, when we run the code, we get results. Right? If you run it just like this, it should work. If you called your data something other than class survival, make sure you change that in there. Now we can go down to looking at these results. So we have our coefficients here. Here's the intercept. Here's the estimated intercept and the standard error of the intercept, the z-value and the p-value of the intercept. This is our sex variable. And the slope, the estimated slope or the estimated effect of sex on survival, the change from female to male is negative 3.5. So females had a slightly higher chance of survival. Here's the standard error of that estimate. It's a very high error, a very small z-value, and a very high p-value. It is not significant. This is the age variable. This is the slope of the age variable. This is the standard error of the slope of the age variable, the z-value, which is the test statistic, and the p-value or the significance of the age variable, also not significant. And then if you look down here, this is the sex M by age. That is the interaction term. And this is the interaction slope. This is the standard error of the interaction. This is the test statistic or Z value, and our p-value here, which is much bigger than 0.05, not significant. They're all bigger than 0.05, so we assume we're using an alpha of 0.05. None of these are significant. Okay, what is the value of the response variable when all explanatory variables are 0? Let's think about that. What is the value of the response variable when all explanatory variables are 0? Well, okay, let's think about our regression equation here. We know that it's y is equal to let's write it intercept. Let's just write it out instead of a. Intercept plus slope 1 times whatever value of x1 plus the slope of your second variable, right? If you have many times, it doesn't like the asterisks in there. Maybe put multiple, no, because I already have x, times the value of whatever x, and so on and so on. So if you were to actually do the math on this, you would say, okay, my y, right, the response variable, let's just type that out actually. Response variable, response is equal to intercept plus slope times whatever value of x you have, plus slope times whatever value of the second x you have. That means your response is equal to intercept. Let's actually put in our slope for the first one, right? Our slope for the first x is negative 3.5, right? Times, I'm just gonna put a multiplication symbol here, times, if our x1 was 0, it would be times 0, right? So it would be negative 3.5 times 0, plus the slope for our second variable, age, which is 0.1305, times 0, if that one is also 0. And then you could also say plus the value for our interaction term, right? Our slope for our interaction term times 0 for age times 0 for sex, right? If all of these are 0, what do we get? Did I tell you I used to teach grade school math when we went over like multiplication tables and zeros and what happens when you multiply anything by 0? You get 0. So you would get intercept plus the slope times 0 is 0, plus the slope times 0 is 0, plus slope times 0 is totally 0, which works out to be response equals intercept. The response variable value when all explanatory variables are 0, right? What is the value of the response variable when all explanatory variables are 0? The intercept. It's the intercept. The intercept, which in this case is equal to negative 36, negative 3.6096. That's the answer. Okay, moving on. A little extra explanation, because some people in class were like, what's that? Okay. This will be on the test, for sure. Which, if any of the coefficients are significant? None. None of the coefficients are significant at the alpha 0.05 because all the p values are greater than 0.05. All the p values are greater than 0.05. So none of the coefficients are significant, right? Write the regression equation by plugging in the coefficients from the model. We kind of already did that above. All right, so logit of y is equal to beta 0. Beta 0 is another way of saying intercept. Plus beta 1 x1, another way of saying the slope 1 or coefficient 1 times whatever x for your first x variable, plus the second slope times whatever value you have for the second variable, plus the beta 3, which in this case is our interaction term, times the value of x1 times the value of x2. Just what we did up here, right? Just what we did up here too. But we didn't put in the interaction term there. We put it in here. Okay, great. And here is the example from our Titanic lab results. Follow that same result. So what we're going to do is we're going to say our regression equation is logit of survival is equal to our interaction term. I'm sorry, intercept. Let me just copy and paste these coefficients down here so I can see them. I'm just going to copy and paste that results table down here so I can see it better. See, I just took that from up top. Just put it down there just so I can see it without scrolling up and down. All right. Logit survival is equal to our intercept. Pop that number in there. Plus, put some parentheses because it's going to be negatives. Plus the slope for sex times let's do it like this. Let's do it minus, let's do it exactly like this. Minus that times sex. It does also happen to be a negative value. So negative 3.6096, which is our intercept, minus 3.5024, which is the slope for sex, times sex, whatever value of sex you have. And plus, let's take our slope for age here, 0.1305 times age, plus the interaction term is 0.2556. And that has to be multiplied by sex and age. It doesn't really like having the asterisks in the, oh, it lets you do one. But if you have two asterisks in the R markdown, it reads it as it should be italicized. So that's why it turns out blue. Okay, so there it is. That's how we write our regression equation. And that's really handy. We'll need that later on. Okay, so now we can ask our question here to interpret the results. How much does the log odds of survival change for every 1 unit change in sex? Okay, remember log odds is just another way of saying logit. Just another way of saying logit. And just remember that odds is equal to P divided by 1 minus P. Probability divided by 1 minus probability. And so the log odds is just the log of the odds, right? And logit is equal to log of odds, right? And in logistic regression, we are actually we actually get our results in logic. We get the logits or the log odds. So how much does the log odds of survival change for every 1 unit change in sex? That's actually this here. That's this coefficient. That's this coefficient. That's the sex coefficient. Okay, so we can say the log odds of survival change by this much, and we can say plus or minus, what's our standard error? Plus or minus this number, that's our standard error. Plus or minus this much for every 1 unit change in sex. And there's only 2 units for sex. There's male and female, 0s and 1s. Remember, females are 0 because it's in alphabetical order and it starts with 0. Right. And we can go to the next question. How much does the log odds of survival change for every 1 unit change in age? We do the same thing. We just go up to age and we say, okay, here's the estimate and the standard error of age. I'm just going to grab them both at once and I'm going to say the log odds of survival changes by this 0.13 0.05 plus or minus. Plus or minus 0.1233. I put standard error. Let's put standard error because sometimes people use confidence intervals, but I put standard error just so you know. Plus or minus this much. For every 1 unit change in age, which the units in our case are years, right? We could have had months or days or hours or minutes. Anyway. So how could we use the above results to answer our original question? What was that question? Oh yeah, we wanted to know questions. Oh yeah, controlling for age, is survival significantly different between the two sexes? No. Let's just take all these questions and let's just put them down to the bottom. This is put them down there and we'll answer them. Blam, 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 knock them out. Okay, how can we use the above results to answer our original questions? So, controlling for age, survival, not significantly different between the two sexes. And here is where you need to, right? You just edit that sentence. That was your question. If you clearly state your question, then answering the question is pretty straightforward. Controlling for age, survival is not significantly different between the two sexes. How do we know? Well, because if you look at this sex M here, you can see that the p-value is much greater than 0.05. So let's add this here. Let's take the z-value and the p-value and we'll put it inside these parentheses and we'll say z equals negative 0.211, comma, p equals 0.833. Kind of goes off the screen here, but see that? That's how we do it. And we can also say controlling for the sex, is survival significantly related to age? Now we can answer that and say, well, no, controlling for the sex, survival is not significantly related to age. And again, we're going to open up our parentheses here, grab that z value and p value that tells us our significance from the output, put it inside the parentheses, and say z is equal to 1.059 and p is equal to 0.290, right? In case anyone questioned us later on, like, how do you know it's not? Well, because we got the z value and this p value, that's how we know. Is the relationship between age and survival different between male and female students? Well, no. The relationship between age and survival is not different between male and female students. And then you can go say, here's our interaction term. And you can even really be specific here. Interaction of sex by age is got a z equal to 0.312, right? That's what this is right here. And a p equal to 0.755, period at the end. That's a complete sentence, yay. Okay, so this is how we can use our results to answer it. You can like tidy this up to make it into a little paragraph as well, because if you were writing results, you're not just writing bullet points, but maybe if you're writing a report, you are. Okay. That's how you do it. The next thing we want to do is make predictions. Make predictions about the future. What's going to happen? Let's try using the regression equation to calculate the odds of survival for a 20-year-old female. How do we do that? Pretty easy. plug in the coefficients from the regression equation above to calculate the log odds of survival of a 20-year-old female. Again, remember that female is equal to 0. So where's our regression equation? Well, we wrote it out up here. We wrote out our regression equation right here. Logit survived, our slope, age, all that. We can just copy that and paste it down into the chunk. So you see that's the regression equation, but I can't call it logit survived with parentheses. That's going to be too confusing. We can call it logit survival. And let's say it's a 20-year-old female, right? 20 femme. Logit survival of a 20-year-old femme. And we could use equal to, or we can use our standard little arrow and a dash. Intercept, right? Minus our slope here times sex. I'm going to put these all in parentheses to keep them tidy. And here we're going to say times, so that's the asterisk. And the value for sex here is 20, right? Because we want to know about, oh no, sorry, sex. The value for sex is 0 because we want to know about a female. Minus the slope of the regression on age times the value for age, in this case, 20, minus the slope of the interaction term times the value for sex, which is 0, which is going to make everything here 0, and the value of 20 for age, put that all in parentheses. So you see, now we have basically 4 terms that are being added together. We're just doing basic arithmetic. It's addition, subtraction, and multiplication. We take the intercept plus, in this case, it's minus because it's a negative term. Oh, I think I messed something up here. Yeah, I did. Age is not supposed to be negative here. This is supposed to be a plus. You guys, you see that? Oh no, but that was from the Titanic lab. Oh, did I grab it all from the wrong place? I did. I was supposed to grab the one that wasn't green. This is ours. Okay. Okay, now I'll show you how to do it again. Logit survival. Femme or 20-year-old femme. Maybe I should edit this video. Okay. Plus the negative of sex. And again, the sex variable is replace sex with 0. Plus the slope for age and multiply that slope by the age of 20. Plus the slope for the interaction term and multiply that interaction term by the value for sex, which is 0 for females, and the age of 20, because that's what we want to know about. And now again, we have these 4 terms. We have this intercept, the slope for sex times 0, the slope for age times 20, and the slope for the interaction term times 0 times 20. And when we run all that, what it gets us is the logit of the survival for a 20-year-old female. If we want to be able to see it, copy and paste that down below, run that, and we get negative 0.9996. That should be the answer you get. But that is the logit of survival. If we want to go from logit, which is log odds, to odds, we just exponentiate it. So to exponentiate it, we use this code syntax. The exponentiate function and our calculated y. Our calculated y in this case is called logit survival 20 femme. So put that down there and copy that. Then type in exp, open parentheses, and copy in the name of the variable that we calculated. Run that, and we get 0.3680266. That is the odds of survival for a 20-year-old female. If you wanted to look at the odds of survival for a 20-year-old male, you would only have to change one thing. You change it from male. You change this from a 0 to a 1. And you change that from a 0 to a 1. And you can see that the odds of survival for a 20-year-old female is less than 1, and it's 0.996, and it actually slightly better for the males. And if you exponentiated that value, you would see that there's a difference, right? The odds of survival for a 20-year-old female are only about a third, and the odds of survival are 1.8 for a male. But for me, odds are a little bit hard to think about. Probability is a lot more intuitive, maybe for you too. But anyway, we can answer this question. What are the predicted odds of survival for a 20-year-old female? The predicted odds of survival for a 20-year-old female is 0.36, right? The odds go up if you're male. But we didn't ask that. I just did this. Now let's use the predict function to predict survival probability for the entire data range for everybody. Step 1, first, create a new data frame with the response variables we want. So now we're going to get all males and females of all ages that we had in the class. Here is the code syntax. Copy and paste this code syntax into your chunk and replace the variables with the right variable names. Calling it new data is just fine. The function here is expand grid, keep that. But instead of x1, what we want it to be is sex. And we want to get all the unique values from class survival for sex, which is male and female, right? And this x2 is age. Where we had all of them. Sex and then age. Sex and then age. That's our x1, our x2. And we're going to get all the unique values of age from, not from my data, that doesn't exist. We're going to get it from class survival age. And if we run that, then we see the first bunch of values. If you get rid of the head, if you delete where it says head and just look where it says new data, get rid of head and take away the parentheses, then you'll see these are all the new data, and you can see for every value of sex, we have the values of ages. We also have it here. You can look at it in the spreadsheet. For every sex, for every age, you can sort it by age, female, male, 18, 19, 20, up to 52. You gotta have an outlier. Okay. To make a prediction for each one of these, female 22, male 22, for each one of these, we can put them all into the predict function and do it all at once. We don't have to type it all out, do the math for each one. We just copy and paste this predictions code into the chunk below and use the predict function. Now here, log results, this is where it's going to ask for whatever is the name of the thing where we stored our results. And we didn't call it log results. We just called it results, right? We just called it results. So just change that to results. New data is what it's asking for, and we did call our new data new underscore data, so that's fine. Type equals response, that's good, leave that, because that's what says, hey, I want you to back transform from the logic to a response variable that makes sense, and it's going to back transform to our probability. And if we run this, then you can see we get our predictions. If you look at all the predictions, there they are. So this is the prediction for our 22-year-old female. This is the prediction, predicted probability of survival for our 22-year-old male. It goes in order like that. But right now it's just saying 1, 2, 3. It's a little hard to tell what's what, right? Like, what does this all relate to? So let's combine this table that has sex and age with this vector of number that has the predicted probabilities and put them all together so we can see what's what, right? Easy. Here's our code syntax. The predicted results, let's just take this code syntax. Let's just take this code and we'll copy and paste it down into the chunk. We're going to get something called predicted results. And what it's going to do is cbind, which is just column bind. It's going to connect all those 3 columns into one thing. It's going to take our new data, boom, those 2 columns, and it's going to add to it the predicted probability predictions. Oops. Oh, the problem is this head result. We didn't call it result. We called it predicted results. We got to change this to head predicted results, and then we'll see the top of it. There you go. There are our predicted probabilities of survival for males and females of every age that we had in the class. It's just showing us the top of it. If we wanted to see all of them, we could go over here to predicted results and we could see the whole spreadsheet. For every age that we had in the class, here's our probability of survival. Okay, so what is the predicted probability of survival for a 20-year-old female? And why is this different from what we calculated above? Okay, so let's go over to our spreadsheet. We'll see what we got. For a 20-year-old female, our predicted probability of survival was 0.269 and a bunch more numbers. The predicted probability of survival for a 20-year-old female was this much, right? And like round it. 0.269. Why is this different from what we calculated above? Think about it. What did we calculate above? What we calculated above was the odds. We exponentiated the logic. And when you exponentiate the logic, you get odds. Probability divided by 1 minus probability. But when you use the predict function with response, you actually get probability. You get the P out. And so you should use some toilet paper, I guess. So anyway, the reason it's different is because we back transformed the variable another step, right? The reason it's different, the reason the numbers are different is because we calculated odds of survival and the predict function gives us probability. Different numbers. So we can go on to graph the results. We can use the predicted probabilities to make a lovely graph like we did in the Titanic lab. Remember the Titanic lab? We made this really nice graph. Nice graph here. predicted probability of survival by age and sex, right? That was really nice. Can we do this for our data? Can we look at us in the same way? Yeah, we're gonna do that right here. Watch. You're gonna write this code. Here is the code syntax. Library, ggplot, you should already have this installed if you're using the same computer. Just copy and paste all this code into the chunk below. And we'll have to change it around, but let's look. ggplot is fine. Predicted results, yes, that's what we called it, right? That's what we called this data frame where we have our data, right? Our sex, age, and predicted probability. The static here, the X is our numeric variable. What's our numeric variable again? Oh yeah, age. The Y is still our predicted probability, so keep that like that. The color is our categorical variable. What's our categorical variable here? Oh yeah, sex. You can use this template with whatever, just helps you remember X is your numeric variable, color is your categorical variable. We're going to use the geom line to make the lines. And the labels, we're going to have a title, a very nice title, come up with a very nice title like predicted probability of survival in our biostats. X is our numeric variable that'll go on the x-axis, and this is age in years. And Y is our predicted probability. Leave it like that. You can change the color scale if you want. You can make it like instead of blue, you can make it green and orange. I'm just going to leave it what it is right now. So blue and red, run that. Takes a sec. And then we can see for the females, which are blue, and the males, which are red, this is the predicted survival probability for the people in our class. Predicted, right, with age and sex. So you can see that as people got older, their probability of survival increased. Of course, we've got like a big outlier over here. So if you took me out with, I don't know, there might still be something going on. But it wasn't a significant effect, even though it looks like it was different. Maybe if you had a much bigger sample size, or you had anything that would actually make an effect. Because just playing a game, it's random. We wouldn't really expect to have an effect. It's just a random effect. Let's go on to writing our conclusions and further questions. So how can you explain our results? Why do you think we got the results that you did? Well, you could write for yourself. Well, it was a game that we played. We don't really expect to see an effect. So of course, that's why we didn't have any significant effects. And then what other questions could we ask? And if you look at the data that we have from our original class data, we also had data on pulse. We had data on major, class standing, number of classes taken for statistics. And maybe as your response variable, instead of survival, you could have another binary variable like maybe whether they got an A in the class or not, yes or no on that. And you could try to see, well, or, if you're going to do a logistic regression, it has to be a binary variable. If you wanted to do a multiple linear regression, you could use like overall score in the class. Is that determined by sex or age or previous class stats experience? Maybe, I mean, if you've taken this statistics before, maybe it's easier to do now, probably, right? So go ahead and write your questions that you want to write. That's it for the video. Thank you so much. And yeah, if you like it, if you want to subscribe, and then you'll be notified for future videos in case I forget to email you and let you know what happened. All you have to do now is knit. So knit and submit, knit to HTML. And hopefully it'll do that for me without too much difficulty. Did it work? Did it work? Oh, yeah, it came up over here though. It came up in the viewer over here. Hopefully that doesn't work it like that for you. It'll work out and you can just go ahead and it'll knit to HTML and you can submit it to La Lima. Have a wonderful weekend.